Good afternoon, everyone. Welcome to Canspy, a platform for auditing CAN devices. We are currently in South Seas CDF with Jonathan Christopher DeMay and Arnaud Lebron. So before we begin, we have a few brief notes. Stop by the business hall located in Bayside AB during the day and for the welcome reception from 5:30 to 7 tonight. The Black Hat Arsenal is in the Palm Foyer on level 3. And be sure to join us for the Pony Awards in Mandalay Bay, BCD, at 6:30. Also, thank you for putting your phone on vibrate. It makes it easier for the rest of us to ignore the ringing while you wait for your voicemail to pick it up. Now, on to the presentation.
Go. Welcome, everyone. Thank you for coming for this talk. We are going to talk about a tool we are actually using on security audit, and we are releasing it here at Black Hat, hoping that other people will start using this tool. So first, the reason behind this talk. We are both security auditors from Airbus Cybersecurity, in an internal team dedicated to cybersecurity stuff, including audit and penetration testing. So obviously we are doing penetration testing for the Airbus group, but we like to help other industries, like the car manufacturers in Europe. Lately we've been working with European car manufacturers to help them find vulnerabilities in ECU. We are not going to talk about that. We're not going to release vulnerabilities we have then found. However, we are going to talk about methodology and tool. How you can work with car manufacturer to efficiently find vulnerabilities in ECUs. What is the methodology behind, and what are the tools needed to apply this methodology. So I'm guessing here some people already know what is penetration testing. Just to be sure we are on the same ground, I'm going to do a brief recap. So basically, it's a methodology for audit. The idea is to find the risk of intrusion, of penetration. However, unlike conventional auditing approaches, we do not review anything. We do not have access to anything. We do not review source code, diagram for architecture. We just place ourselves in the shoes of real attackers and start auditing, testing a given scope. That's why we talk about the black box approach, because like a real attacker, our target is a black box for us. We do not have any knowledge of its internals. The idea behind this approach is to get really relevant results because you really place yourself in the shoes of real attackers. That means that when you find the vulnerabilities and you exploit it, you know really what is the actual impact of exploitation, how hard it is to exploit it, what is the level of attackers needed to find it and to exploit it. It's called exploitability. And this is really the main advantage of using this approach. However, there are limitations because compared to real attackers, we have more constraints. Usually we have less time because we are costly resources. We work on the bill. Usually we also have less resources actually. And we also have more ethics. That means that we cannot damage, at least we have to do whatever is possible to not damage the scope we are auditing. Something a real attacker really does not care about. That's why more than black box, we talked about gray box. The idea is to ask the customer, the stakeholders, whoever is asking us to do penetration testing, to provide us with just enough information to level the playing field between us and a real attacker, to compensate for these additional constraints we have. So that's gray box approach. And done properly, we do not fall back into white box approach when we review things. We're still working using actual tests, but we are able to compensate for these additional constraints. This is something that is very welcome by stakeholders because usually they have a huge scope of responsibility that is usually changing continuously, and they need to find to improve security as much as possible with a limited budget. So they welcome really the penetration testing methodology. They like the gray box. They provide us with just enough information. But they do not ask us to do penetration testing on anything. They have to rely on risk analysis, identify within their scope what is the most critical part that needs to be audited first, or that needs the more resources for auditing.
So what about car manufacturer? So they are mostly focused on safety for years. And now they also start to focus on security and cyber security. Why? So first of all, they add a lot of functionality to the car. Now a car is not just something that transports you from a point to another. They have entertainment, navigation, a lot of options, and also remote connection. And so the exposure area are increased a lot. They also start to use more and more software. If you think about Tesla, we can see it's a lot of software in the car. And, well, again, this increases the possibility of vulnerability. But the real reason why is mostly about security researcher. And if you look on the internet, we can see some security researcher publication and something to be concerned about, because when your car can be crashed remotely, it's a big concern for a car manufacturer. So they start to really focus on security and to take that into account. So they proceed as for standard penetration testing. First of all, they conduct risk analysis, what is exposed, what are the consequences, the cost, etc. And they prioritize the electronic control unit focus. So the electronic control unit is basically a controller in your car that can control the dashboard, the engine, the brake, etc. It can have 70 to 90 EQ in one car, or even more. So they are all connected to a bus, a CAN bus, mostly. So we'll talk about that later. And after that, they saw they have to select which EQs they will work on it from a security point of view, which are exposed or critical. And they conduct penetration testing. And of course, they carry out corrective action. So some EQ are common to several vehicles from the same manufacturer, or even for different manufacturers. So it's more logic to think about EQ and not from a vehicle, since if you have vulnerability in an EQ that is common to several vehicles, it's more efficient to fix the EQ. So also the corrective action. So we all think about if there are a vulnerability that is found and the car is already sold, the constructor have to recall, maybe can do software update remotely, like Tesla, but this is also a source of vulnerability. But recall is not just the only consideration. If, for example, they do the penetration testing of the EQ, but the car is already in production or in ramp-up, they will have, for example, so this can make the production flow different, because, for example, if they use a debug port such as JTAG to set up an EQ for a model or for an option in the production flow, and in the paint test we demonstrate that you should use a secure way to do that with password, authentication, etc. This can change a lot the way they produce the car and they assemble the car. Another issue is they do not do the EQ themselves. They subcontract. Sometimes have subcontractor of subcontractor. So making a patch can be time-consuming and costly. So the corrective action can be more complex than for standard software on the IT world. So, good.
An additional word about ECU being common to multiple vehicles. Actually, it's even worse than that because since there are few suppliers for ECUs, it's not unlikely to find a vulnerability that will be common to different ECU using the same basis from different car manufacturers.
So where we begin? We begin with exposed EQ. So basically what is connected. So mostly the infotainment and navigation. So we have Wi-Fi, Bluetooth, USB. So nothing new here. It's not specific to car. It's common to everything using Wi-Fi or Bluetooth. But however, you will still need a CAN tools to sniff the CAN bus and see what is happening when doing your test. The car also mobile broadband connectivity for software updates or for remote diagnostic, even in case of emergency, if the airbags are triggered, so this contacts the emergency. But again, it's standard broadband system with conventional protocols or TCP, etc. And again, nothing really new here. It's not specific to car. So now what is really interesting us here is when you have found a vulnerability in an exposed EQ, but most of the time this EQ, since it's for infotainment and not critical application, it is not directly connected to the engine, the brake, or something really critical. It's on another bus, another CAN bus. So when you have access to this infotainment or not critical CAN bus, you want to do lateral movement and try to have access to this critical bus. For that, you can do reverse engineering of your protocol or try to break the security access challenge. So this will give you access to some features of the EQ. So we call that a debug mode or a higher privilege. You can have access to other settings of the EQ, and this will obviously give you more access to the car. Yeah. So CAN architecture. So this is an example of the most simple CAN architecture you can find. You have several EQ. So in the CAN specification, there are colored nodes, what's basically the same. They are all connected to the same bus. The priority mechanism is quite important. When several EQ are sending a packet in the same time, the priority is managed by the ID. So the lowest ID has the higher priority. So if two is talking in the same time, the one with the lowest priority will be sent and not the other. As you can imagine, you can have big congestion issue if everyone try to talk if every EQ try to send packets in the same time, only the one sending packet with an ID with high priority will be sent. And so low priority ID EQ will never talk, in fact. And another last point about CAN is about the acknowledge. The acknowledge system is not an acknowledge of frame receive, but since every EQ can do the acknowledge, it's an acknowledge that just says that the frame has been sent in the good way, not that any EQ have really processes it. Yep.
The idea here was not to go deep into the detail of the CAN protocol. Actually, you can just go on Wikipedia. You will have all the information you need. But these three particular points, the ID-based priority mechanism, the congestion issues, and the acknowledgement by everyone, are three key points that we will have to deal with. We'll see later when dealing with the man-in-the-middle setup that we need to audit one particular ECU. So keep these three main key points in mind because they will be useful for every next slide almost.
Yeah, and even if it's the simplest architecture, this is not really what you will find in a car. As I said earlier, on a car you will have several CAN bus that segment everything. So multiple separate bus. So this is one example. You have several EQ. Some are only on one bus. Other can be on two or more bus. So if you think as an attacker, what you will focus on is the EQs that are on several bus, and you can maybe use as a bridge to reach the critical EQ you want to. And on another example of architecture.
Just one word. For example, why there wouldn't you would need one ECU to be connected to multiple buses? This is by design actually. If you think, for example, of navigation system, they will need to give you direction, so they need to be connected to the infotainment buses to send you audio indication, but they want to display the actual speed of the car, so they need to be also connected to the engine buses to have this information, and this is why it's not possible for all ECUs to be on only one buses.
Yeah. So, and now something that is more, I think, the state of the art, it's having several buses with gateway, like you can find on classic IT network. The gateway will forward or not the packet function of the ID, but not only. They can be more smart and, for example, use the situation of the car. Is the car is running, is the engine is on, is the engine is off, and function of this situation, they will allow ID to go from a bus to another or not. So clearly we can see something we can play with.
A classical example of this is if you use a diagnostic tool from the car manufacturer, from the OBD2 port, and you have automatic tests to test a lot of things. For example, wheel parallelism. The tool can actually send CAN frames to test the parallelism of the wheels, and a gateway would not allow such frame to be forwarded to the wheel bus if the car is actually driving at 100 miles an hour, for example. It checks that the car is actually stopped before allowing this kind of frame to be forwarded from one bus to another.
Yeah.
So as Arnaud said, once you compromised an exposed ECU, the next step, so from the risk analysis, the next type of ECUs to audit is ECUs that are connected to multiple buses or the gateway, because they are the target, the next target for an attacker who wants to move from a less critical bus, like the infotainment bus, to a more critical bus, like the engine bus. There are several attack vectors. The goal is not to go into the details, but we work with three main categories of CAN attacks. First, it was simply using the own capabilities of an ECU. For example, a remote diagnostic ECU, by definition, has the ability remotely to send frames that will be forwarded across multiple buses. Or you can reverse engineer higher layer protocol and find conventional parsing vulnerabilities that if you know how to, if you work on the exploit, at some point you do compromise the ECU. And of course, the security challenge. That if you find a way to identify as a security authorized tool from the car manufacturer, you can do almost anything with most ECU, as far as completely reprogramming them. However, if you work without the help of the car manufacturer, achieving this kind of attacks is very time consuming. You have to locate ECUs, you have to dismember them and try to find on-chip debug interfaces or directly unsolder EEPROM chip and worked on to extract the firmware. And once you do, this is really actually the hard part, you start on reversing the firmware and try to identify vulnerabilities and try to understand how you can craft an exploit to use on these vulnerabilities. If we compare this to the conventional IT world, in most situations we try to avoid this. We try to find vulnerabilities with less work. If I take as example the web application, you do not reverse engineering all the communication between the client and the server from ground zero. Usually you use a legitimate client, insert yourself in between, let the legitimate client do the heavy work, and when you feel it's right, you start modifying packets, replaying packets. And the idea is really to insert yourself at the right moment, and this way you do not need to reverse engineer all the communication between the client and the server. In theory, that should be applicable to a CAN ECU. The CAN ECU is receiving and sending frame, so we might be able to intercept them at the right moment without understanding the whole communication from the get-go. This is something, for example, we can do with an ECU for remote diagnostic. Since we are working with the car manufacturer, again, think of gray box. We can ask for the remote diagnostic tool that is provided to auto mechanics. And this way, we can let the tool do all the communication. And since we are able to intercept, and if we are able to intercept the frame between this particular ECU, then we can, at the right moment, start playing with the frames. Also, another way to do this is just to work on an ECU without the car at all, and to build an environment to simulate the car and work on in your lab. This is the very idea of setting the man-in-the-middle setup. You, unlike a conventional IT network, you will need to physically cut the bus or unplug one particular ECU, build one bus dedicated to this particular ECU, and set up the man-in-the-middle between the two buses. So again, you can do this in your lab by emulating the other ECUs, or you can ask, again, the help of the car manufacturer. Usually, all car manufacturers have integration bench when they try their prototype ECUs. It's easy to access the bus, it's easy to unplug an ECU. So working with them, it's quite easy to set up the man-in-the-middle approach if you have the proper tool. And that was our limitation when we wanted to work this way. If we take a look at the existing tool, first, we have to keep in mind that the CAN protocol was designed to comply with timing constraints. However, most tools only have one CAN interfaces. So to do the man-in-the-middle setup, you will need to use two of them and bridge them together with the host computer. But such setup would add high latencies, and that would defeat the timing constraints. If you find a tool that has multiple interfaces, you have then to be sure that the microcontroller that is used by the tool is quick enough to handle all the frames that need to be forwarded between the different buses. On that front, most tools will use, because it's quite easy to and quite practical, a UART, usually over USB connectivity. However, at best, if you follow the standards, you are far from the needed bit rates to follow just, for example, an OBD2 at 250 kilobits per second. And you have to keep in mind that CAN buses can go as far as 1 megabit per second, and we need two of them, because again, we have two distinct interfaces, at least if we want to set up a man-in-the-middle approach. So again, UART is not at all a solution to do this. Finally, they provide with their framework, which is good. You not only need the hardware, you need the software to interact with the tool. However, as security editors, again, that need to work fast because we are costly resources. We really prefer to use proven and standard framework. And the idea is not to build a new framework, which we did not do that at all, but to interface your tool with a known and proven framework, or at least design it in a way that will make it compatible natively. So with all that in mind, and from there we are starting to talk about the tool, we set several objectives. The first one was to have two, and that is obvious again, two distinct CAN interfaces, because again we need to forward frames from two CAN buses without necessarily using a host computer. We need to be able to forward the packets between two buses, but also we need to be able to modify, drop, replay, filter them in any way you want, guaranteeing the low latency and being able to handle the full bitrate of the CAN protocol. So again, 1 megabit per second. That's why we choose actually a connectivity that is well deployed in any computer nowadays, the Ethernet. 100 megabits per second is more than enough to handle even the worst case of man-in-the-middle setup for two CAN buses. And we wanted also our tool to be somewhat autonomous. So we'll see later that it can be powered over the 12 volts power source of the car, but we wanted to add an SD card reader so it could read, write a packet from and to the SD card and also store different parameters and the whole configuration of the tool on an SD card.
So about Canspy hardware, our main goal was to use as far as possible component of the shell and cheap one, of course. Why component of the shell? To avoid you or anyone who want to use our tools to have to do complex soldering, which require tools and knowledge. So our baseline is a STM32 microcontroller with a discovery kit that is less than $20, and you can find it on every provider such as Mouser or DGK. And why we select this is because it has two CAN interface. This is not like, for example, when you have an Arduino with Shield and the Arduino is connected to a CAN driver with SPI or serial, and the CAN driver is managing the logical layer of CAN. In this case, the logical layer of CAN is managed by the microcontroller itself. You just need electrical adaptation. Yeah. Then we have a shield that provides all the connectivity we need. So as Jonathan said, we need serial, we need the Ethernet, and SD card, and also chip. So less than $40 again, so on the same provider. And we did not find any shield or shield for CAN already built. So we have to build it ourselves. So you will have to do some soldering, but really easy. And so on the shield you have the two connectors for the CAN interface. You have plenty of jumper to set up the shield in several mode function, of if you are on the car, or if you are on the touch bench, etc. So you can also select your supply from 12 volt from the car, from a USB, etc. And again, it's cheap. So less than $30, I think, for the PCB and the component, and it can really be soldered by anyone with a solder machine.
I suck at soldering personally, and I can solder this one. So
Would be good.
a few words about the firmware that is running on top of this hardware. Like I said, we really wanted to be compliant with timing constraints. We really did not want to drop any frame. We really wanted to be able to manipulate packet without disturbing as much as possible the behavior of the ECUs, the ECUs that run the bus, including the one we are auditing. So we had to rely on real-time approaches to meet that goal. The idea with this slide just to explain to you that if you want to add new functionalities to the tool, it's quite easy. We have at the bottom an abstraction layer to handle input-output operation with the hardware. So you don't need to worry about this. There's an API dedicated to this. To be sure that your new functionalities will not induce frame dropping, if you comply with the design, that is one functionality is one service is associated with one device, and a service can either be an asynchronous one or synchronous one. The synchronous one handling the input-output events, they are given an absolute priority thanks to an upper layer scheduler, and that's it. Basically, you can add a new service. You use the abstract layer. You make sure you comply with these rules, and you can add the new functionalities without impairing the current performance of the tool. here I'm going to go a bit into the details of the tool. Like I said, for example, we want to be autonomous, so there's a filtering engine that is embedded in the tool, so you can either choose to filter the frames on the computer using the Ethernet port, or by providing rules to the tool to the engine directly. You have like I said, every functionality for each functionality is one service. The idea here, even if all services are enabled, you still have good performances, but the idea is always to enable only what you want, to configure the tool for the specific case you are trying to set up. That's also the reason you have so many jumpers on the dual can shield. Obviously, the source code of the firmware is open sourced. If you want to add new functionalities, and let's go a bit into the details of the services. It's quite straightforward, actually. You have the CAN services, donc one services to forward, one services to filter, and one services to inject, if you want to inject a frame through other services or through the network. Through the Ethernet, you have the wiretap services that just sniffing CAN frames over the network. The bridge services does that too, but allow you to inject frames through Ethernet. The SD card allow you to capture a frame if you want, for example, I don't know, to hide the tool in your car and go to your auto mechanics and want to see
what's happened.
Want to see what kind of frames are being sent by the tool you do not have access to. I forgot to write it, but you have also a replay service if you want to replay frames from the SD card. The logdem service is basically for debugging purposes. You have the exactly same services on the UART connectivity, the log view services. The monitor services is basically to monitor what's happening on the buses. Again, the UART connectivity is slow, very slow compared to a CAN bus, so be careful and you be sure you know what you're doing when you're using this service. And of course, an interactive shell to do all the configuring. A few words about the CAN devices, not the services that are running for CAN devices, but the CAN devices. By that I mean the devices handler themselves. Since we have two distinct devices, we have two distinct devices handlers. That means that we have a whole three services: forward, filter, inject, for duplicated for both devices. That means that you can, for example, forward frames from CAN 1 to CAN 2 while you are filtering them from CAN 2 to CAN 1, or you can just drop them or do whatever you want. We support all standard PID for the CAN bus. A few words about one particular point we made great care to implement. When you are setting a man in the middle situation, we will modify the behavior of the ECUs. The idea is to have less impact as possible on their behavior. We talked at the beginning of the three key points from the canvases. You have congestion issues. That means that most ECU will not try to determine what is the rate they should send frame. They will just send as much frame as possible and let the priority mechanism do the throttling. But if you plug out one ECU to make it have its own CAN bus, it will have the whole bus for itself and will send a whole lot of frames that you will not be able to forward on the other bus because, again, of the priority mechanism. If you consider, again, we do not want to drop frame, so we did not like that situation at all, but it's even worse if you consider packet fragmentation. Some information are being sent over multiple CAN frames, they are fragmented. If you do not forward all of them, you will send garbage to the other bus. So the first mechanism to do this is just to stop acknowledging frame. If you remember the key point, an ECU will want its frame to be acknowledged before sending another one. Until a frame that has been sent has been acknowledged, it will send it again and again for reliability purposes. So if you stop acknowledging on one bus until the last received frame has been properly forwarded to the other bus, then you prevent the ECU you are auditing to sending more frame. Very simple to understand, but you have to be able to control the acknowledgement mechanism at microcontroller level to be able to implement this option. It's just a true-false option on the tool, but there's a bit of work under there. For the very same reason, if you drop frame, for example, because you had rules to drop frames, from one bus or from the other, you will again reduce the number of frames in the bus, and you will give more bandwidth to the other ECUs that will again start sending more frame that you can forward to the other bus. The other option here is when you drop a frame is not to actually drop it, but it's to send a dummy frame instead. Instead, the tool will send a different frame with the same level of priority, the same length, but with zero data in the frame. And by using these two options, you can actually set up a man-in-the-middle situation with an ECU on its own bus, with not with zero impact on behavior for all ECUs, but with as less possible impact. A few words if you want to understand how to process the information that is being sent over Ethernet. Again, the idea was to be compatible with existing tools. So the CAN information is sent over Ethernet using the socket CAN format. It's natively supported in the Linux kernel. It's natively supported in Wireshark. You just need to tell the tool that you are using a particular data type, the 88B5, that is free for local experiments. And you just need to tell the tool that, and you will have a native Canspy support for the tool. To be able to distinguish between frames that are coming from the first or the second interface, we just simply use MAC addresses from the Ethernet format. Just consider that we are allocating one MAC address to the tool and one MAC address to each CAN interface. And from that, it's quite easy to send the frame to either one of the bus, or to understand from which CAN bus an actual frame was received. For example, if you want to pass a socket CAN format through Ethernet with Scapy, you have less than, I don't know, 15 lines of code. And for Wireshark, you just need to tell the tool that the dissector that's already built in the Wireshark has to be used when the iter type 88B5 is received. We spent most of this talk saying that to apply this methodology, you need to work with the car manufacturer. Unless you want really to take apart your car, it's really easier to work with the car manufacturer to unplug a device or to cut the CAN bus. However, there's one situation when everyone can use the tool. That is the reason we use this particular situation to make a little bit of a demonstration here, even though we actually did not worked on the OBD2 case professionally. That is the OBD2 case. The OBD2 port is just a port everyone can access on this car. That is a direct line to one CAN bus. There are several tools that are available to use the OBD2 device. You have the car diagnostic tool. You have the insurance company that are starting to provide with OBD2 dongle to monitor the driver behavior. And you have even law enforcement now that are not only using sensor in your exhaust pipe, but also now are checking your ECU directly. So that's why we argue this is actually an interesting case. If you were able to compromise this type of device from a malicious car, then you can compromise potentially sensitive network these tools will be connected to, or for example, other cars. Car diagnostic tool will be plugged to many cars. If a malicious car can compromise such tool, it put at risk the other cars. So it's quite really simple for anyone to try this use case. You don't need to cut anything. You just need to build a female OBD2 port and plug the Canspy in between the car and the OBD device you want to test.
So a quick demonstration to show what you can do with Canspy. We have a bench with a Canspy that is used to emulate an EQ. Basically, he take request of information and send answer. So it's a simulator. We have a Canspy in man in the middle, which is forwarding the frame for CAN1 to CAN2 and from CAN2 to CAN1. And we have an OBD2 dongle that is sending the information to a smartphone with Bluetooth. I hope it will work. Yeah, so this is the smartphone. I hope you can see the speed. And so if Jonathan changes the speed in the simulator, so in this case, we want to show how it is easy if you know something about the frame and if you have already done some reversing. To emulate an EQ, and this is something that could be useful if you want to work without your car, because it's quite convenient to work in your office and still that in your garage.
Just for information, we're working with a cheap
cheap Bluetooth dongle that
Chinese,
is disconnecting, and it's really slow to reconnect.
Okay.
Yep. So yeah. So.
I think now we have an issue.
Yeah, it's a demo effect. So, sorry. You will have to try it yourself. So, thank you everyone. And now if you have questions, we have a backup video, but we are running out of time, so let's jump to question.